everyone, my name is Jacqueline Castro. I'm a fellow classmate in this summer statistics course. My final project analyzed the possible relationship between female height and female shoe size. I gathered this random sample of 30 values for each, 30 values for female height and 30 values for shoe size. I moved the female height over to my summary sheet. I decided to focus on the female height and summarize those values, and I calculated a z-score for each and every one of these heights represented in inches. I discovered that the mean was 62.77 inches. The mode had a single mode of 65 inches, a mid-range of 60 inches, and a median of 63 inches. And because this distribution, so I constructed this distribution chart, this histogram, because the distribution was, I would say it's roughly bell-shaped, even on both sides. I decided and it's not left or not skewed to the left or right, it's pretty even. I decided that the most relevant measure of center was the mean, and that the closest value to the mean was 63 inches. As we can see, it is the closest value to 0, meaning that the closer it is to 0, the closer it is to our mean. And when referencing the Chebyshev's rule, which states that at least 75% of our data should fall within 2 standard deviations for any distribution, my sample exceeds that, and that is because when I calculated my lower and upper fences, the 53.125 and the 72.125 inches, I discovered that I had a single outlier. So one out of my 30 data values, one out of my 30 heights, which is 3.33% of my data, falls beyond 2 standard deviations from the mean, but the rest of the data values, the rest of the 29 female heights, 96% falls within 2 standard deviations above or below the mean. And my sample obviously exceeds that rule. Moving on to the confidence interval for proportion, my task was to use my sample and estimate the percentage of adult females who are over 62 inches tall with a 90% confidence interval. So I used the 30 values of female height, and I just highlighted in red if they were over 62 inches. I discovered that 16 out of my sum of 30 female heights were over 62 inches. 16 over 30 gave me this p-hat value, the 0.5333 decimal value, and I used this to calculate my margin of error, which gave me these lower and upper values. These percentages I plugged in the p-hat, multiplied it by the, I believe, q-hat, so 1 minus this p-hat over 30, my 30, total 30 data values, square root that and multiply it by my critical value down here, and then add or subtract that to this initial p-hat value. Margin of error, add it to the p-hat or subtract it to get these values over here on this right side. I decided that I am 90% confident that the true percentage value of females who are taller than 62 inches is between 38.4% and 68.3%. Moving on to my hypothesis test in reference to mean. The task was to use your sample, test the claim that the mean female height has significantly changed from what it was in 2018 CDC report, which was 64 inches. So it's asking that I test if it has significantly changed from 64 inches. So from my sample, female height, I have a mean height of 62.7667. The claimed female height was in 2018 was 64 inches. We're testing it at a significance level of 5%. Now, because this probability value is greater than the 5%. I decided that using this sample, there is not enough evidence at the 5% significance level to conclude that the mean female height has significantly changed from the 2018 CDC reported mean of 64 inches. Moving on to copy of correlation. This is where we use both female height and female shoe size. I mean, visually on this chart, we can see something positive, and that's visually, and this correlation coefficient also kind of supports that theory visually. It's closer though to 1. It's moving upwards, positive, it's moving upwards, and it's closer to 1 than it is to 0. But it's asking, determine if a significance linear correlation exists between the shoe size of a female in the US, the shoe size a female in the United States wears, and their height. I said yes, based on the results, the data supports that there is a significant positive linear correlation between female height and shoe size. Because the correlation coefficient is R is 0.70878, which is greater than 0.5, this shows a strong relationship, and this tiny probability value, 0.000012, is significantly smaller than the significance level of 5%, 0.05, we can reject the null hypothesis of there being no correlation between these two variables. Second task was to use the results of the correlation to estimate the height of a female in the United States that wears a size 10.5 shoes. This regression model is following a slope-intercept form, y equals mx plus b. The output is y. We're going to represent this with y. And so I kind of had to do some backwards math. So 10.5 equals the slope times the height plus our negative y-intercept. So I added our negative y-intercept to this left side to add it to the 10.5 shoe size. That gave me 19.11697, which should equal the slope times the height. Now, if we divide both sides by the slope, we should get the height, which gave me 73.54 inches. So the height of a female in the United States with a shoe size of 10.5 has an estimated height of 73.54 inches. And this is the third task was definitely a lot easier. Then estimate the shoe size of a female who is 75 inches tall. So I just plug in 75 to this box and I got 10.88 as the shoe size. That is the estimated shoe size. Which of these two estimations would you tend to believe more and why? I said I lean more towards the calculation made using height, the 75 inches, specifically because the regression model was designed to predict shoe size and not the other way around. So that is my final project, and I hope that I was able to explain myself well and that you guys understood it. But I look forward to seeing everyone's project and answering some questions. And thank you guys. And that is it for my final project.